Hey guys, starting off 2.5, we're going to look at implicit differentiation. So we'll explore what this word means in a second, this implicit. One thing that we can look at is what does explicit mean? So if you look over here to the right at the end, this explicit form is when you have y equals. Okay, so we'll compare explicit to implicit in a second. Again, normally we started taking the derivative. We have y equals, so what we would do here is we would say the derivative of y with respect to x is 8x and we're done. Well, look at this next equation, y to the fourth plus xy equals all this other stuff, and we would try doing the same thing. We would try to isolate y so that we can find dy dx. So look at on the left, they both have a y, so you can pull a y out, and then you're left with y cubed plus x. Now, if you're thinking that we should divide both sides by y, that's not going to work because even if I divide both sides by this y, I still have this y here. So this is a huge uh-oh, and we're stuck. Okay, so and this is where implicit comes in. Okay, so the explicit way that we're used to is not working, so now we need to find an alternative. I want you to look right here at the operator. I keep calling this d over dx operator. It's telling us what to do. So it's saying if we take the derivative of y, we get dy dx. If we take the derivative of x, do you see you get dx over dx? And that's just 1. I don't know if you ever thought about that before, though you guys know the derivative of x is 1, but this is why you get dx over dx. That's pretty cool looking at it that way. Okay, so sometimes you're interested in finding the derivative of an equation that's not allowed to be solved for y. And this is when we start looking at implicit. Okay, so we're going to do a side-by-side comparison of both of these functions. Do you see that looking at this, this is the explicit form. If I multiply both sides by x, I get xy equals 2, which is right here. So we're going to use the explicit form because this is what we're used to. So what we're going to do is apply the operator d over dx. So if I have y, I'm going to rewrite it as 2x to the negative 1 because that's calculus friendly. And then we apply the d over dx to both sides. On the left, you can see that you get dy over dx, which is what we're used to. Remember, dy dx is just a way to write the derivative. Now on the left, this 2 is a scalar, so we rewrite that. You are then going to bring the negative down in front and subtract the exponent by 1. Okay, we really don't need to write this operator when we go to take the derivative of both sides, right? We could just say dy dx equals this. I'm doing this to make a point, to show you how the operator is working. And then so then the next step would be just to write your final answer. Remember, we don't want negative exponents, so you get negative 2 over x squared. Okay, now on the right side, we're going to find the derivative of a function, the same function, but written in a different form. So we're going to apply this operator. We're going to need a lot more space. So let's apply the operator d over dx to xy, and let's also apply it to the right. Okay, so on the left now, do you guys see product rule? So you're going to get x, which is the first, times the derivative of the second. So here's the first and here's the second. So if I'm applying this operator to the second by taking its derivative, I hope you can see that you're getting a dy dx. Plus the second, now as I apply this operator, d over dx to the first, I'm going to get dx over dx. Now, we're not going to have to write this again in the future. I'm just making a point showing you how the operator gets applied. What I would really hope you to think, that you would be thinking, is the second part of product rule is second, and what's the derivative of x? Isn't that just 1? The reason it's 1 is because dx over dx. And then if you keep going, look at the right, the derivative of 2 is 0. As I go to rewrite this, remember my goal is to find the derivative, which they call dy dx, which I call dy dx. So now I need that isolated. So what I'm going to do is I'm going to move this guy to the other side, and you're going to get x dy dx equals negative y. And remember, we really didn't have to write this dx to begin with. That was just a 1, so I'm going to leave it like that. Okay, going on. I'm going to divide both sides by x, so dy dx is now negative y over x. Now I'm claiming that we're going to get the same answer, and we didn't make a mistake, but how is this on the right the same thing as the answer on the left? Well, look at this answer didn't have a y in it, so let's see if maybe we can replace that y. If I go over here and solve for y, isn't y 2 over x? So if I replace that y with 2 over x, and then instead of dividing, can't we multiply by the reciprocal? So now I get negative 2 over x times 1 over x, and dy dx is negative 2 over x squared, and then ta-da, we know we're good because we have the same answer. Okay, so the method that we used in the previous example on B, this way right here, is called implicit differentiation. Okay, so we noticed that they were the same, but which one was easier? So what do we notice? They're the same. So which method was easier? I think the explicit. Look at how much less work the explicit had. The explicit had a lot less work because y was already isolated. Okay, so what you're going to do is if you can isolate y and it's not messy, let's always do that. That's what we're used to. Let's try using explicit. We saw up above here though, right? What if we have this crazy thing here? We don't have the option of isolating y, and then we're forced to use implicit. Okay, so what we're going to do is we're going to differentiate both sides with respect to x, and then we're going to isolate dy dx. That's exactly what we did here. We differentiated both sides with respect to x, and then we went through and we isolated dy dx. Okay, I liked applying that operator d over dx, and you can see it right here. Remember dy over dx is also known as y prime, okay? The reason I'm going to have you use dy dx in your work is because you're new to this. And if you replace dy dx with a y prime, sometimes it looks like a y, and then you can make a mistake. I have a tendency to use y prime because it's so much quicker. But again, because we're new, let's stick with this in our work. Okay, so looking at this one, find dy dx. Can we isolate y? We can't, because look, I can take a y out of both, but I still have a y squared here. So this is a case where we're forced to use implicit. So first we're going to look at this term right here. That's product rule. So it's going to be first, what's the derivative of the second? So the derivative of y is dy dx, plus the second, which is y, and the derivative of the first is 3x squared. Okay, now I'm on to this piece. So now I have a first and second again. Product rule, here we go. So first, what's the derivative of x? That's 1, because remember when you apply the operator to x, you get dx dx, which is 1. Plus the second, which is x. Okay, here's the tricky part. Now, when you take the derivative of y cubed, you bring the 3 down. This is chain rule, guys. You bring the 3 down, you have y squared. But there really is an inside stuff there, which is y, and then you write dy dx. Okay, so let me say that again because I feel like that's new. To find this derivative, you bring the 3 down in front and you get y squared. But think about if this had parentheses. You'd be using chain rule. So bring the 3 down, y squared, but then you have to take the derivative of the inside stuff. And what's the derivative of y? It's dy dx. Let's go up here and look at something real quick. If I apply the operator to x cubed, I get 3x squared, and the derivative of the inside stuff, which is this x, is 1, which is dx dx. So we've been using chain rule the whole time, remember? But now if the inside stuff is y, we need dy dx. So we have all that. Now the derivative of 17 on the right-hand side is 0. Now we're going to try to isolate dy dx. So we are going to leave anything dy dx on the left. So that's x cubed dy dx. Plus 3xy squared dy dx. We're going to move anything non-dx to the other side. So I'm going to move this term and this term to the other side, so you'll see that they're subtracted. So you have a negative 3x squared y minus y cubed. This is just algebra. We're trying to isolate dy dx, so I'm going to factor that out and get x cubed plus 3xy squared. Double check that. Equals negative 3x squared y minus y cubed. Now we can finally divide both sides by whatever's next to the dy dx. So our final answer and it's going to look a little messy. This is how a lot of your answers are going to look. They're going to have a y in them, totally fine. Because remember, we can't isolate y, so y is embedded in the problem. Okay, on B, note here that even though y is isolated right here, there's another y here, so that's why this is still implicit. Okay, so if we apply the operator d over dx on the left, we get dy dx. If you apply it on the right, you get the derivative of x is dx dx, which is 1. Now the derivative of secant, I want you to see that this is chain rule because that's not an x. So the derivative of secant is secant tangent, and then the derivative of the inside stuff, the derivative of y is just dy dx. We're going to move all the dy dx's to one side, so we're going to subtract secant y tangent y dy dx, and on the right side we're left with a 1. I'm going to factor out a dy dx. So I have 1 minus secant tangent. Make sure you're writing y there. So then dy dx is 1 over 1 minus secant y tangent y. Okay, so on to the next one. This is really what you're doing the whole time. If anything, it just might get a little messy, but not too bad. Okay, on to the next problem. This is an awesome tip to save you time. Notice here that I'm asking for the derivative at a point, not the derivative in general. So we don't have to go through all this work like we did up here of isolating dy dx. After we get the derivative in this first step, I'm going to replace any x and y with the numbers that they gave me. Okay, if you don't do that, you're going to run out of time possibly on a test or quiz. Okay, so this one is messy. Notice that y cannot be isolated. We have a y on the left, and then also a y with cosine, okay? So we can't isolate y. That means we have to use implicit differentiation. So this is product rule also, because we have a first here, and then our second is here. Okay, let's try this. So first, the second, we're going to use chain rule. The derivative of cosine is negative sine, and you copy that stuff over. The chain rule is the stuff on the inside. Now I have to take that derivative. So that derivative, we have to be careful with implicit. Also, one more thing to note. Do you see that this is dy dt? So our ordered pair is ty instead of xy. So we need to keep our eye on that. I know I have a tendency to accidentally write x's, so double check as we're writing this. So going back to the problem, what we did is we wrote first, right here, derivative of the second. So I need this derivative. I wrote negative sine. Now I need the derivative of the inside, which would be dy dt, because that's the derivative of y. The derivative of t is 1, and the derivative of t squared is 2t. Plus second. So go ahead and write the second down. And the derivative of y, which is the first, is dy dt. The left side is 3t squared. Now, normally we'd want to isolate dy dt, but we're not going to here because they wanted the derivative at a point. So go ahead and sub in 0, 5 pi over 2 for all your t's and y's. Also, I love pointing out here, this is the break in the product rule. So this was first derivative of the second, second derivative of the first. Okay, let's go ahead and sub these numbers in. So everywhere there's a y, we're going to write 5 pi over 2. So negative sine of 5 pi over 2. Lucky for us, t is 0. That's awesome. Then we have dy dt plus 1 plus 2 times 0. And then that big plus sign. And then we have cosine of 5 pi over 2 plus 0 plus 0. Again, lucking out, dy dt. And look here, t is 0. Awesome. Okay, on the left now, we have 5 pi over 2. Let's look at this next step, which is sine of negative 5 pi over 2. I'm sorry, negative sine of 5 pi over 2. So 5 pi over 2, I want you to think of that as 2.5 pi. So 2.5 pi, if you're on a unit circle, here's 2 pi and then another half a pi. So you're up here. Okay, so the sign there is 1, but because there's a negative in front of it, we're going to write negative 1. In the parentheses now, so now guys, I'm on to here. Look what I have. I have dy dt plus 1 plus 0. so just dy dt plus 1. On the right, we just have a nice 0. Okay, so now I have this scalar out in front. Let's divide both sides by this, so it's gone on the left, and then when I divide it on the right, I just get 0. So now dy dt plus 1 equals 0, so dy dt equals negative 1. Okay, make sure when you're doing this that you do not isolate dy dt. Make a big note on your notes as you're copying this over that you only do the first step and no algebra after that. After that, we just subbed all these numbers in and a lot of things went away. Okay, going on to example 4. Again, concepts for the most part are done. This is just going through examples. This is a circle centered at the origin with radius 2. Let's go ahead and sketch this. Okay, so this has a radius 2. We know all the ordered pairs. I'm going to go ahead and fill them in though just in case. 0, 2, 2, 0, negative 2, 0, and 0, negative 2. Sketch the graph, done. Now find dy dx. Now here we could isolate y. Look up here. We could say y squared equals 4 minus x squared. We could take the square root, but I'm going to recommend if y is not isolated to go ahead and use implicit, because then you're going to get plus or minus. Look, we have a square root now. We have an inside stuff that means chain rule. Let's just try using implicit and see if it's okay. We're applying the operator, d dx to everything. So if I have x squared plus y squared equals 4, the first one, let's bring the 2 down on the x, lower the exponent by 1. What's the derivative of the inside stuff? That's a 1. Next one, bring the 2 down, write y. What's the derivative of y? dy dx equals 0. They asked us to find dy dx. I hope you see we could divide everything by 2, and the 0 just stays 0. So now I have x plus y dy dx equals 0. So y dy dx equals negative x. So dy dx is negative x over y. So here is the derivative of x squared plus y squared equals 4. So now it says using calculus, verify that the graph has horizontal tangents. Now, again, this year I want you guys to think of like trigger words. What does it mean to be a horizontal tangent? A horizontal tangent is going to occur, so I'm going to put blue here. Horizontal tangent is right here and right here. That's when the slope is 0. So when you see horizontal tangent, you need to think that's when dy dx is 0. Well, look back at your dy dx. dy dx is negative x over 0. So how could this be 0? It's going to be 0 whenever the numerator is 0. So that would be when negative x is 0, which divide by negative 1, and it's when x is 0. So we just use calculus to verify that when x is 0, we get a slope of 0. But they asked not to verify the x, but the points. So let's go ahead and throw into the equation x squared plus y squared equals 4. Let's replace x with 0. So then y is plus or minus 2. And now we have our ordered pairs at 0, 2, and 0, negative 2. Okay, so we just verified that. Now they're saying, hey, we're not done. We have to verify more. Now you want vertical tangents. Well, what's a vertical tangent? A vertical tangent is when dy dx does not exist. Okay, and when will dy dx not exist? We'll go ahead and look at your equation. It's when y is 0. Okay, so now I'm going to take the equation x squared plus y squared equals 4, and I'm going to go ahead and replace y with 0, giving me an x of plus or minus 2. So now I'm going to have 2, 0 and negative 2, 0, and that's exactly what they said up above. At 2, 0 and negative 2, 0, we'll have vertical tangents. Let's use a different color here. Let's use yellow. So a vertical tangent is right here. Can you guys see that's when the slope does not exist? And that's exactly the points they gave us. Okay, now the next part says at what values of x is the slope 3/4? Well, we have an equation for the slope. Remember, it's dy dx, and that's negative xy. So they're saying when is this 3/4? So 3/4 is negative xy. So that means x would be negative 3/4 y. All I did was multiply both sides by a negative x. But they said at what values of x? We're kind of stuck. All we have is x equals negative 3/4 y. Oh, but remember we have this. We can sub this into x squared plus y squared equals 4. So let's go ahead and do that. We're going to replace x with negative 3/4 y. So now we're going to have 9/16 y squared plus y squared equals 4. If we get a common denominator, can you guys think of this having a 16 over 16? So now we have 25y squared over 16 equals 4. Almost done. Y squared, let's take 4 and multiply by the reciprocal. So now y squared is 64 over 25. Take the square root, we get a plus or minus 8/5. So it said at what value of x is the slope 3/4? Unfortunately, we have y, but that's okay. We can now find x, because remember over here, let me point this out, x was negative 3/4 y. So x is going to be negative 3/4, and y is 8/5 or negative 8/5. So if we do this, we're going to get 24 over 20, or you guys could have reduced inside, and that's negative 6/5. You also have to sub in here negative 3/4. Remember, we could have had a negative 8/5, and that will give us a positive 6/5. So they just asked for x, so our final answer is going to be plus or minus 6/5, because look here, let me point this out, we got 2 answers. Okay. This is day 2, but we're actually going to put this all together. So if you're also asked to find a higher order derivative, I'll walk you through that paragraph as we go through this. So to find y double prime, given this, okay, we're going to go a little quicker through this since we've seen some of these. We know we have implicit because we have a couple y's. Now, could we have isolated those y's in this case? Sure, but we're going to go ahead and practice using implicit. The derivative of 4y, 4 is a scalar, and the derivative of y is dy dx. We have to use product rule for xy. So x, which is the first, times the derivative of the second, plus the second, which is y, times the derivative of x, which is 1. You don't have to write that 1. And the derivative of 5 is 0. Look here on the left. These two are dy dx. So we are going to get rid of the other number. So we're going to have 4 dy dx plus x dy dx. And go ahead and get rid of that y by moving them to the other side. Factor out a dy dx, and you have 4 plus x equals negative y. Therefore, dy dx is negative y over 4 plus x. So if you're asked to find a second derivative, I want you to go ahead and find the first. Now we're going to take that derivative. Okay, so to take that derivative, this is quotient rule. I'm going to start using now y double prime and y prime. Again, we just have to be careful that we don't mistake y prime for y to the first. Okay, so now if I go to take the second derivative. Okay, so the second derivative, we're going to go ahead and write y double prime. And remember, quotient rule, so low d high, d high, d high, there's d high, minus high, d low, d low, d low. And the derivative of the bottom is 1. All over low, low, so 4 plus x squared. Now this dy dx right here, we can't have, we have to get rid of this, but look at, we're going to replace it with that dy dx there. So y double prime is going to be 4 plus x, and then I'm going to have a negative, but then when I throw dy dx in, do you guys see that's a negative y over 4 plus x, so that's going to be positive. Then I have plus y over x plus 4 squared. So our final answer, kids, let's see if we can squeeze this in. Do you notice that canceling? So we're going to have a y on the top, that's it, plus this y is going to give us 2y over x plus 4 squared in their second derivative. So please make sure that after you get to this step where you find the second derivative, you're not done, you have to replace dy dx. Okay, last two. Find an equation of the normal line. What does normal line? Remember, normal line is perpendicular to the tangent. Okay, so let's go ahead and find this derivative. What we're going to do first is rewrite it as 1 over 32x squared plus 1 over 8y squared equals 0. To find the derivative, we're going to bring the 2 down to give us 1/16 x, bring the 2 down to give us 1/4 y to the first, and then the derivative of y is y prime. I'm going to start using y prime now. Remember, we don't want the derivative in general, so we're not going to isolate y prime. We want it at the point 4, 2. So go ahead and replace x with 4, replace y with 2. So now I'm going to have 1/4 plus 1/2 y prime. If you subtract 1/4 to the other side, you get 1/2 y prime is negative 1/4. So y prime, if you multiply both sides by 2 to get rid of this, you're going to get negative 1/2. Now this is the slope of the tangent. So that means the slope of the normal will be, that was y prime, we got to be careful with that, is going to be 2 because it's the opposite reciprocal of what this is. Okay, so now if I go ahead and make my tangent line, which is my final answer, it's going to be y minus, look at, they gave me the 2 here. The slope of the normal is 2. And then x minus, what did we have? We had a 4. Okay, last one. Determine an equation of the tangent line at the point 3,1. Again, we've done some stuff like this. This is just an extra for practice. So to take the derivative of the left, we're going to apply the operator, just like we've been doing, d over dx. We're using implicit because we can't isolate y. Okay, so to take the derivative, 3 stays, that's our scalar. I'm looking right here now. This is chain rule. I'm going to bring the 2 down in front, rewrite the stuff on the inside. And if you remember when we did this, I always highlighted the stuff on the inside. Okay, so we're writing the stuff of the inside, which is x squared plus y squared. Go ahead, decrease the exponent by 1. Now we have to multiply by the derivative of the inside, which is 2x plus 2y y prime equals 100 is a scalar. Let's write it. And then you have x y prime, so first derivative of the second, plus the second, which is y, derivative of the first, which is x. Again, guys, we're at a point, so we are not going to go ahead and solve everything for dy dx. What we're going to do instead is say at this point, so at 3,1, and find the derivative. So we have a 6. We're going to replace x with 3 and y with 1. And then we're going to replace x with 3, y with 1. Let's see if we're missing a parentheses. I think right here. Equals 100, x with 3, y with 1. Okay, let's see what this leaves us with now. Right here, this is 10 times 6 is 60. So we have 60, 6 plus 2y prime equals 100, 3y prime plus 1. We could divide both sides by 10 if we wanted, just because you can see the scalar out in front. Both have 10s. Let's do that. So we're going to have 6 plus 2y prime equals 10, 3y prime plus 1. So now I'm going to have 36 plus 12y prime equals 30y prime plus 10. Throw all the y primes on one side. So if you can see, it would be this and this. And then put your constants or your non-y primes. They don't have to be constants on the other side. So now I have I'm going to have 12y prime minus 30y prime. So what I did is I subtracted this over. Then I'm going to have 10. And then do you see this 36? I'm going to subtract that over. Okay, let's move this down a little bit. So now I'm going to have negative 18y prime equals, what is that? Negative 26. So then y prime is 26 over 18. I got rid of the negatives. So y prime is 13 over 9. So final thing of the day is going to be y minus. Go back up here and look at your ordered pair. So y minus 1 equals the derivative at 3,1, which is 13/9 times x minus 3. We are done with 2, 5. See you guys later.